Hello, my name is Simon Schneider. I'm a senior researcher and lecturer at the University of Science Technicum Wien in Vienna, and I'm studying and teaching concepts and models for climate neutral buildings and districts. In this series of videos, I will show you how to use our tool for positive energy district modeling, simulation, and assessment. Over the course of these videos, what you will learn is how you can model and assess your positive energy district project, which data you will need, how the tool compares to other district energy modeling approaches, how to interpret the results, and how to avoid common pitfalls. The requisites for taking this course and these videos is that you have some basic familiarities with energy modeling and building energy systems in general. So let's start with the introduction and have a look at the energy systems that our model can assess. First of all, here you see a positive energy district in a classical system boundary where we include and look into building operation and building use, which means we take into account all the energy that is required in the district for heating the floor areas, for cooling the spaces, the domestic hot water required to use the areas, be it for residential use, office use, or what have you. So this first is the so-called energy demand for operation of the buildings. That is included in the model. And then secondly, we have the local renewable energy sources that can be generated on site. This is the second important aspect of the positive energy district, and it is included in our model as photovoltaic generation inside the district. And then finally, and optionally, we also have a so-called context factor, which means that the energy balance assessment is also taking into account certain factors of density and whether retrofitting of the district is a topic to be taken into account. And then this is the first system boundary, and then the second one is the positive energy district including mobility. It's pretty much the same as the first system boundary, but we include also everyday mobility with private cars, scooters, e-bikes, etc. So here we also include the mobility that is required to reach the district. And also optionally, we can also include the context factor for this mobility, meaning how much energy is available from offsite sources to account for that. The model does not include so-called embodied energy and embodied emissions, which means energy and emissions that are generated by producing the building materials, producing the components that are required to build, maintain, and refurbish districts. This is not part of the system boundary. This is not part of our modeling. So if you are interested in this, then you will need some additional tooling to model and assess that. What our tool does is basically an hourly simulation of all energy flows. The hourly modeling of energy flows, including electric mobility, is necessary to understand the impacts of so-called sector coupling, which means the interplay between the building sector and the mobility sector and the energy generation sector. The interplay is very crucial for understanding how much renewable energy can be used on-site but also off-site. And this is only fully understood if we are taking a picture that is taking hour by hour the situation at hand and understanding where the energy comes from each hour of the day and throughout a whole year. So this includes flexible use of electrical and thermal storage systems like batteries, electric vehicles, but also thermal storages like thermally activated building systems where you heat up the concrete core of buildings to store electricity and energy, and also domestic hot water tanks to thermally store electricity. So let's start at the tool that we have developed for this course and how it situates and compares to other tools. Now, positive energy districts are complex systems that need careful, integrated planning across various fields and disciplines. On the other side, assessing positive energy districts with a comprehensive approach, including building use, mobility, and embodied energy, is challenging. Current dynamic models such as IDA-ICE, for example, or Energy Plus, Transis, which are very detailed and can have a very comprehensive look into very small spaces from individual building rooms all the way to whole districts, are often not practical for early planning stages where there is simply not enough data and a lot of uncertainty to efficiently model these districts with these tools, where it would be too time consuming and too resource consuming to do this. This difficulty arises mainly from the lack of data needed for detailed energy simulations. And even with enough data, these detailed models are often too resource heavy for early use, since planning changes can invalidate their results quite quickly. So simpler decision support systems, on the other hand, that you have on the right-hand side, where you have a lot of coverage and accessibility, such as statistical analysis that look into the energy balances on an annual basis or a monthly basis, they might miss important details about positive energy district flexibility aspects, the cogeneration aspects, or they simply fail to cover all the necessary energy flows and only focus on, let's say, heating and building operation, but not include mobility, for example. So in this triangle, we try to situate ourselves in the very center, where we strike a deal between accuracy and resolution. We go for a very high temporal resolution. We sacrifice some of the spatial resolution compared to very high detailed physical building energy models like Transis, IDA-ICE, Energy Plus, etc. But we also try to have the same extent and coverage as some aggregated frameworks, while still be accessible and simple enough to be used for by non-building physicists, by people that are not energy engineers. So let's now look into the design principles that have been guiding us to developing this tool. So the framework design is based on observation from district implementations in the last couple of years. In the early planning stages of positive energy districts, many project details are still unknown, and building designs can change very frequently. It is important to be able to iterate through these changes very rapidly to quickly find configurations that are interesting and that can be developed further. So our work aims to create a simulation and assessment framework that is easy to use, that can be repeated often, and that meets the positive energy district definition, so it exists and can be internationally compared. It tries to cover all aspects of district operation and use, mobility, the embodied energy and emissions, with enough detail to be useful in early planning. We also have some papers published on the theoretical basis of these PET definitions that you're invited to have a look at. Now, the assessment tool aims to provide the following key features. First, it tries to reduce model creation costs. It implements a principle of default first and input later approach. And by using extensive defaults, mostly from Austrian building code and scientific literature, it is easy to quickly gain an insight of the district's overall performance get some first indicators and quantitative results, while still being able to be further refined later in the future. Second, we try to reduce the data transformation costs, which means that we try to provide an easy interface for copying and pasting data from other sources, such as energy performance certificates, passive house planning packages, which are typically and in many cases available for building and district projects. Thirdly, we try to enable simple and fast scenario creation, which is facilitating quick iteration through the different district scenarios. So we can have a look into more of what interests us and find out what kind of scenarios are actually interesting. Fourth, we try to ensure easy iterability, trying to make it simple to iterate within the planning process. Fifth, we also try to promote accessibility and transparency by avoiding the use of proprietary tools and software. We try to make algorithms and data open access, ensure that the calculations are transparent for the users, also for those without any programming knowledge and programming skills, which is also differentiating this tool from other tools in this area. And then we try to allow for easy extensibility and customizability by ensuring that the simulation model can be easily extended and customized by practitioners, which is also thanks to the implementation as an Excel tool. And finally, we try to provide a comprehensive planning tool where we try to offer a one-stop shop framework for planning evaluation, quality assurance and verification, minimizing data transfer requirements, and so on. And with this design, we try to ensure a user-friendly, efficient, and transparent framework for early positive energy district planning. So the tool that I'm about to show you is basically an interface that allows for quick input of your district specifications into a more comprehensive simulation framework underneath that is hidden by default, but that you can access if you want to delve deeper and try to model more detailed and investigate further scenarios. And the documentation for this is also can be found online.